Hey everyone, and welcome back for another deep dive. You're ready to go microscopic today. We're going to be talking about imperfections in solids. That's right, all those tiny flaws and quirks that actually make materials so interesting. You sent us a chapter from the textbook Material Science and Engineering,
Mm.
an introduction, and a really cool article all about catalysts. So we're going to be exploring why these imperfections matter, how they shape the materials all around us, from the steel in bridges to even the catalytic converters in our cars.
Yeah, it's funny actually. A lot of people think, they think a perfect crystal exists, but actually every single solid material has imperfections. They exist at the atomic level, and they're surprisingly important too. These imperfections aren't always bad. In fact, they often are what dictates how that material behaves.
So even something like a diamond,
Yeah.
a diamond which just looks flawless to us, it's
Yeah.
actually full of all these imperfections when you zoom in. That's crazy. The textbook mentioned these things called vacancies, basically missing atoms in the crystal structure. And it said that near a material's melting point, there can be a ton of these vacancies, like 1 in every 10,000 atoms is just missing. Why are there so many of these vacancies allowed?
Well, think about it like this. Imagine a stadium packed with fans for a big game, right? Even in a sold-out crowd. There are always a few empty seats here and there, and it's kind of similar in a crystal lattice. You're always going to have some empty spots, especially as the temperature rises.
Okay, so these vacancies are kind of like those empty seats, just part of the natural arrangement of atoms.
Exactly. And they're not just empty space. These vacancies actually play a really important role in how materials actually function. For example, they allow atoms to move around within the material, which is essential for processes like diffusion, electrical conductivity. No vacancies would mean no electrical current.
Whoa. Something as simple as a missing atom can affect something as important as electrical conductivity. That's pretty amazing.
Yeah.
I also read about these self-interstitials, which are atoms that are crammed into spaces where they don't belong. It's kind of like trying to squeeze into a packed elevator.
Yeah, it's a good analogy. They're like those people on the train that try to cram on, when it's already full. And they cause a lot of strain, a lot of distortion in the crystal structure because they're forcing themselves into these spaces that are already occupied.
That makes sense. So I'm guessing these self-interstitials, since it's so crowded, are pretty rare compared to vacancies.
Yeah, they're much less common because it takes less energy to create a vacancy than to force an atom into a tight space. And nature kind of favors the easiest way, so arrangements that require less energy. That's why you see many more vacancies than self-interstitials.
Okay. So we've got these missing atoms, these atomic stowaways. They're causing all these disruptions in the otherwise perfect crystal. What happens when you introduce foreign atoms into the mix? Kind of like mixing different ingredients in a recipe.
Yeah, that's a good way to think about it. When we introduce foreign atoms, we're creating what are called impurities. And these impurities can either replace some of the original atoms in the crystal, that's called a substitutional impurity, or they can squeeze into the gaps between the original atoms, which is called an interstitial impurity.
This is like swapping out one ingredient for another, or adding a dash of spice to the recipe. The textbook used the example of carbon in iron to explain interstitial impurities. Why is that such a classic example?
It's the basis of steel. Carbon atoms are much smaller than iron atoms, so they can fit into the spaces between the iron atoms in the crystal structure. And these tiny carbon atoms act like a glue, like atomic glue, making the iron much stronger and more durable. That's why we use steel for everything, from bridges and skyscrapers to cars and appliances.
So the strength of steel is literally due to those tiny carbon atoms squeezing in between the iron atoms. That's incredible. But how do material scientists even know which atoms will mix well together? Is it just trial and error, or is there some kind of science to it?
There's definitely a science to it. There's a set of guidelines called the Hume-Rothery rules, and these help predict whether two elements will form a solid solution, which is a mixture where the atoms are evenly distributed. These rules consider factors like atomic size, crystal structure, electronegativity, and the number of valence electrons that each atom has.
Valence electrons, those are the ones in the outermost shell of an atom, right? That
Yeah.
determine how it bonds with other atoms.
Exactly. And those tiny particles have a huge impact on whether two elements will work well together or not. For example, copper and nickel, they have similar atomic sizes, crystal structures, and valence electron configurations. So they form what's called a substitutional solid solution. They can basically swap places in the crystal lattice without causing too much disruption.
So it sounds like there's a lot of chemistry involved in understanding how these imperfections behave in solids.
Absolutely. The interactions between atoms and their electrons are key to understanding why some impurities fit in easily, while others cause major disruptions. Now let's move on to another type of imperfection. Let's talk about dislocations.
Dislocations. I'm picturing like a fault line in the Earth's crust, a place where things get shifted out of place.
Yeah, that's a pretty good analogy. Dislocations are what are called linear defects, meaning they occur along a line. Within the material structure, think of it like a wrinkle in a fabric. There's two main types: edge dislocations and screw dislocations.
Okay, so let's iron out these dislocations. What makes them different?
Okay, so imagine a deck of cards, all neatly stacked. An edge dislocation is like having an extra half card inserted into the deck, creating a step or a ledge. A screw dislocation, on the other hand, is like a spiral ramp, like a parking garage. If you can picture the structure of a parking garage, you'll have a good picture of a screw dislocation.
So edge dislocation is a sharp disruption, while a screw dislocation is a more gradual shift
Hmm.
in the arrangement of the atoms.
Exactly. And these dislocations, they're incredibly important for understanding how materials deform under stress.
Yeah.
They're the reason why metals can be bent and shaped.
Wait, so without dislocations, metals would just be brittle,
Mm.
and we wouldn't be able to work with them. That's fascinating. But how do dislocations actually allow metals to bend?
Think of it like this. Imagine you're trying to slide two rugs across each other. If the rugs are perfectly smooth, they'll stick together and be difficult to move. But if there's a wrinkle in one of the rugs, it's much easier to slide them past each other. And similarly, dislocations allow planes of atoms in a metal to slip past each other much more easily when a force is applied.
So those tiny wrinkles in the atomic structure are what give metals their flexibility and allow us to shape them into all kinds of useful forms. That's pretty amazing. Okay, so we've covered point defects, impurities, and these fascinating dislocations. What other surprises does this hidden world of imperfections hold for us?
Let's zoom out a bit and consider interfacial defects. These are imperfections that occur at boundaries between different regions within a material.
Boundary. So the zones where different crystals meet,
Yeah.
or where there's a change in the orientation of the atoms.
Exactly. Like a quilt, made up of many different patches of fabric. Each patch is perfectly fine on its own. But the seams where the patches meet create a slightly different texture. And in a similar way, the boundaries between different regions in a material can have a significant impact on its overall properties.
So even though each individual crystal might be perfectly ordered, those boundaries where they meet can create a whole new set of imperfections.
That's right. And one of the most common types of interfacial defects is a grain boundary. You see, most materials aren't actually single crystals. They're made up of many tiny crystals, or grains, all stuck together. And the boundaries between these grains are called grain boundaries.
Okay. But if these boundaries are zones of mismatch, wouldn't that make the material weaker? Like if the seams in a quilt are weak points, wouldn't a material with a lot of grain boundaries be more likely to fall apart?
It's a good question. It might seem counterintuitive, but materials that have many grains, we call those polycrystalline materials, they can actually be incredibly strong because the bonds between the atoms across those boundaries are still strong, and having many small grains can sometimes make a material tougher by preventing cracks from spreading easily.
It's like a network of tiny barriers that stop a crack in its tracks. So grain boundaries can actually improve a material's strength and toughness. I'm starting to see that these imperfections aren't always a bad thing.
Exactly. Now, there are different types of grain boundaries, depending on how the crystals are oriented relative to each other. When the misorientation is small, we call them small-angle grain boundaries. And these can even be described in terms of arrays of dislocations, those linear defects we talked about earlier.
Wait, so dislocations can actually form the boundaries between grains. That's a crazy connection. It's like the atomic world is full of these intricate relationships.
Absolutely.
Yeah.
And when the misorientation between crystals is larger, we call them high-angle grain boundaries. And these boundaries are more jumbled and disordered, and they can have a big impact on how the material behaves, especially at high temperatures.
It's amazing how these different types of imperfections, from missing atoms to misaligned crystals, all contribute to a material's unique characteristics.
And we haven't even talked about surfaces yet, which are another type of interfacial defect that plays a crucial role in how materials interact with their environment. But we can save that discussion for the next part of our deep dive.
That sounds great. I'm already amazed by how much we've uncovered just by peering beneath the surface of materials. So before the break, we were talking about all kinds of imperfections inside materials and how they can actually make things stronger. I always love those moments where we can like bust a myth. And it sounds like surfaces are another one of those cases where what we see isn't really the whole story.
Exactly. Surfaces might seem like they're outside the material, But they're actually full of imperfections that have a huge impact on how the material behaves.
Okay, so what's so imperfect about a surface? I mean, I'm picturing something like a polished tabletop. It looks pretty smooth to me.
Well, at the atomic level,
Mhm.
even the most polished surface is a crazy landscape. You see the atoms at the surface. They don't have the same number of neighbors as atoms that are deeper inside the material. So they have these unsatisfied bonds. They're kind of like reaching out for something to connect with.
Well, it's like they're missing a dance partner at the atomic party.
Exactly. And those unsatisfied bonds, they create what we call surface energy. And this energy makes surfaces very reactive. They want to bond with something to lower that energy and become more stable.
Is that why things get dirty? Dust and grime sticking to surfaces
Yeah.
to satisfy all those lonely atomic bonds?
Exactly. And it's also why metals corrode. Those surface atoms are eager to react with oxygen from the air, and they form these oxides that can weaken the metal over time.
So even something as simple as a surface can be a hotbed of activity at the atomic level.
That's pretty wild. Speaking of reactivity, I'm really curious about that article you sent on catalysts. I always thought they were like these magic ingredients that just make reactions go faster. But it sounds like imperfections play a key role here, too.
Oh, absolutely. Catalysts are all about speeding up chemical reactions, but they do it in a very specific way. They provide an alternative pathway for the reaction to happen, one that requires less energy. And guess what? Surface imperfections are often the key to making this happen.
Okay, now I'm really interested. How do those tiny imperfections on a surface help a chemical reaction go faster?
So those imperfections, things like steps and kinks and vacancies, even those unsatisfied bonds we were talking about, they create these things called active sites on the catalyst surface. These active sites are like little pockets of high energy where molecules can bind and interact more easily.
So it's like the imperfections are setting the stage for a molecular meet and greet, where reactants can bump into each other and do their thing. That's a great way to picture it. And by bringing the reactants together in just the right way, the catalyst lowers the energy barrier for the reaction to occur. So it speeds things up, but without actually being consumed in the process.
That's pretty neat. The article mentioned this material, I think it was Ca.5, 0.502, that's used in catalytic converters in cars. Is that a good example of this? How these surface imperfections work their magic?
It's a perfect example. Catalytic converters are essential for reducing harmful emissions from car exhaust. They contain catalysts, often made of materials like that one you just mentioned, that have a huge surface area
Yeah.
with tons of imperfections, like jagged mountains at the atomic level.
So I'm picturing those exhaust fumes full of nasty pollutants flowing through the catalytic converter and encountering this mountain range of a surface. What happens then?
As those pollutant molecules hit those active sites on the catalyst surface, like carbon monoxide or nitrogen oxides, they get temporarily trapped. And this allows them to interact with other molecules, like oxygen, and rearrange themselves into less harmful substances, like carbon dioxide and nitrogen gas and water.
So those tiny imperfections on the surface
Yeah.
are literally cleaning up the air we breathe. That's pretty amazing.
It really is. It just shows how important it is to understand the role of imperfections in how materials behave. We can't just focus on the perfect structure. We have to embrace those quirks and flaws because they often hold the key to unlocking some amazing properties and applications.
Okay, we've covered a lot of ground. We've gone from missing atoms to extra atoms, to dislocations and grain boundaries and surfaces, and we've seen how these imperfections can impact everything, from a material's strength and flexibility to its reactivity and its ability to even clean up pollution. Is there anything we've missed in this microscopic world?
There are other fascinating imperfections, like what are called bulk defects, like pores and cracks. These are much larger imperfections, and they can really affect a material's strength and durability. And then there's atomic vibrations, those tiny jiggles and shakes that are constantly happening, even in materials that seem completely solid.
Atomic vibrations sound like a dance party I want to learn more about.
It's definitely a lively topic. But for this deep dive, we've focused on those structural imperfections that play such a big role in defining a material's character.
And it's such a fascinating character. I'm starting to see that imperfections aren't just flaws to be avoided. They're essential features that give materials their unique personalities and make them so useful in the world.
You got it. Understanding and controlling these imperfections is really the key to designing new materials and improving existing ones and tackling some of the biggest challenges facing our planet.
It's a whole new way of looking at the materials around us. Instead of seeing them as static and unchanging, we can appreciate the dynamic world of atoms and imperfections that's constantly buzzing beneath the surface. It's pretty amazing. I definitely have a newfound respect for this intricate world of materials. A huge thank you to you for taking us on this deep dive today. It's been an incredible journey.
The pleasure was all mine. And a big thank you to you, the listener, for suggesting this fascinating topic.
We hope you've enjoyed this exploration into the hidden world of imperfections in solids. Don't forget to share your thoughts and questions with us on social media or through our website. We'd love to hear what surprised you the most, or what other aspects of materials science you'd like us to explore in future deep dives.
And remember, the next time you see a seemingly perfect object, take a moment to appreciate the bustling world of atoms and imperfections that lie beneath the surface.
Until next time, keep diving deep. It's amazing to think that something as simple as, a solid material can be so complex at the atomic level.
It really is. It shows you how much we still don't know about the materials that make up our world.
Totally. And it also makes you realize how important material science is. It's a field that's often overlooked, but it's essential for solving so many problems.
Oh, absolutely. It's at the heart of so much innovation. Developing new energy sources, creating more sustainable materials, even advancing medical technology. It all depends on materials science.
Yeah, it's incredible. And, as we continue to explore and understand these imperfections, it seems like we're unlocking so many possibilities for designing and engineering materials with totally new properties.
Yeah, that's the exciting part.
So the next time I see a bridge or a smartphone or a piece of pottery, I'll be thinking about all those tiny imperfections that we can't see.
Mm-hmm.
The missing atoms, the misplaced atoms, the dislocations, the boundaries, all working together to give that material its unique character.
It's a whole new way of looking at the world around us, isn't it?
It really is.
We can see beauty and complexity in things that we might have just thought were simple or even flawed before.
Absolutely. Well, I definitely have a newfound respect for the world of materials. A huge thank you to you for taking us on this deep dive. It's been an amazing journey.
My pleasure. And a big thank you to you, the listener, for sending in this awesome topic suggestion.
We hope you've enjoyed this exploration into the hidden world of imperfections in solids. Don't forget to share your thoughts and questions with us on social media or through our website. We'd love to hear what surprised you the most, or what other aspects of materials science you'd like us to explore in the future.
And remember, next time you see something that seems perfect, take a moment to appreciate that hidden world of atoms and imperfections that make up everything we see.
Until next time, keep diving deep.